Right now, somewhere in America, a machine the size of a building is crawling across the earth, leaving behind a perfectly smooth ribbon of concrete road. It moves slowly, deliberately, and with a precision so extreme that the surface it creates is flatter than a sheet of glass. This is not ordinary construction. This is American road building at its most advanced, a process so refined, so technologically sophisticated that engineers from around the world travel to the United States just to witness these machines in action and study how they achieve the seemingly impossible. The numbers behind American concrete road construction are staggering. The United States maintains over 4 million miles of paved roads, more than any other country on Earth. And the concrete highways that form the backbone of this network are engineered to carry loads exceeding 80,000 pounds at speeds over 70 miles per hour. Every year, American engineers pour enough concrete to build a road from New York to Los Angeles and back again, multiple times. The machines that make this possible consume hundreds of tons of concrete per hour, moving forward at a steady, relentless pace that never stops during a pour. But building a concrete road is not simply pouring gray sludge onto dirt. It is one of the most precisely engineered construction processes in existence. Every layer must be exact. Every measurement must be perfect, because a road that fails does not just crack, it kills. The process begins months before any concrete is mixed. Survey teams, equipped with GPS systems accurate to within 2 millimeters, map the entire route. They measure elevation, drainage patterns, soil composition, and existing utility locations. Every detail is recorded digitally, creating a complete three-dimensional model of the road to be built. Geotechnical engineers drill test borings along the entire proposed route, extracting soil samples from various depths. These samples are analyzed in laboratories to determine bearing capacity, moisture content, and frost susceptibility. The data determines how the road foundation must be prepared to prevent settlement, cracking, and premature failure. Road design engineers use sophisticated computer modeling software to calculate the exact concrete thickness, reinforcement requirements, and joint spacing for every section. Variables include expected traffic volume, percentage of heavy trucks, climate conditions, and design life. Most American interstate highways are designed to last 40 years or more. The concrete mix itself is engineered with extraordinary precision. Portland cement, fine aggregate, coarse aggregate, water, and chemical admixtures are combined in exact proportions, calculated to produce specific strength, workability, and durability characteristics. The target compressive strength typically exceeds 4,000 pounds per square inch after 28 days of curing. Chemical admixtures are added to control the concrete's behavior during placement. Air and training agents create microscopic bubbles that protect against freeze-thaw damage. Water reducers improve workability without weakening the mix. Retarders slow the setting time during hot weather, allowing crews more time to finish the surface before the concrete hardens. Every batch of concrete is tested before it reaches the road. Slump tests measure consistency. Air content tests verify freeze-thaw protection. Cylinder samples are cast and lab tested for compressive strength at 7 and 28 days. If any batch fails testing, the entire load is rejected, no exceptions. Before the first drop of concrete touches the ground, the roadbed itself must be prepared with surgical precision. This foundation work is invisible to drivers, but it is arguably the most critical phase of the entire project. A perfect concrete surface means nothing if the ground beneath it cannot support the load. Massive earth-moving machines begin the process. Motor graders with 12-foot blades sculpt the raw earth to precise elevations. GPS-guided systems control the blade automatically, maintaining grades accurate to within a fraction of an inch. The operator monitors screens while the machine does the precision work impossible to achieve by human hands alone. The subgrade soil is compacted using vibratory rollers weighing over 20 tons. These machines send powerful vibrations deep into the earth, densifying the soil particles and eliminating air voids. Nuclear density gauges are used to verify that compaction meets minimum specifications. Insufficient compaction means future settlement and road failure. Above the compacted subgrade, a layer of granular base material is placed. This layer, typically 6 to 12 inches thick, consists of carefully graded crushed stone that provides drainage, structural support, and a uniform surface for the concrete slab. The base material is spread by machine and compacted to exact specifications. In many modern projects, a layer of hot mix asphalt is placed on top of the granular base. This asphalt-treated base provides additional support and acts as a moisture barrier, preventing water from rising into the concrete slab from below. Every layer in the system serves a specific engineering purpose. Some projects use geotextile fabric between layers. These industrial-strength synthetic sheets prevent fine soil particles from migrating upward into the drainage layer, which would clog it and compromise its function. The fabric is rolled out by machine and overlapped at seams to create continuous separation between incompatible materials. Steel dowel bars and tie bars are placed before concrete pouring begins. Dowel bars are smooth, round steel rods that transfer load between adjacent concrete slabs at transverse joints. Tie bars are deformed steel rods that hold adjacent lanes together, preventing them from separating over time. Each bar is positioned with millimeter precision. The dowel inserter is itself a remarkable machine. It automatically places dowel bars at exact spacing and depth into the fresh base material ahead of the concrete paver. Hydraulic mechanisms push each bar to precisely the correct position. Misaligned dowels cause joint failure and premature road deterioration, so accuracy is critical. Now comes the star of the show, the concrete slipform paver. This is the machine that transforms liquid concrete into a finished road surface in a single continuous pass. It is one of the most impressive construction machines ever designed, and its capabilities border on engineering artistry. A modern slipform paver is a massive machine, weighing over 100 tons. It rides on crawler tracks positioned outside the slab edges, spanning the full width of the road being paved. Some machines can pave lanes up to 50 feet wide in a single pass. The width is adjustable to match project specifications. The paver is guided by a string line or, increasingly, by three-dimensional GPS systems. Total stations or satellite receivers mounted on the machine communicate with onboard computers that control elevation and alignment in real time. The machine knows exactly where it is and exactly where the road surface should be, to within fractions of an inch. Concrete arrives at the paver in a continuous stream. Dump trucks or conveyor belt systems deliver fresh concrete and deposit it in front of the machine in a carefully managed windrow. The volume must be precisely controlled. Too much concrete causes pressure problems. Too little creates voids. The supply chain runs with military precision. As the paver moves forward, the concrete enters the machine through an open front section. Inside, a series of auger screws and vibrators distribute the concrete evenly across the full width of the slab. The augers spread the material laterally, while powerful internal vibrators consolidate it, eliminating air pockets and ensuring uniform density throughout. The vibration system is critical. Arrays of hydraulic vibrators operating at specific frequencies liquefy the concrete momentarily, allowing it to flow around reinforcement steel and fill every void. The frequency and amplitude are precisely calibrated. Too much vibration causes segregation, where heavy aggregate sinks and weak paste rises to the surface. Behind the vibrators, a conforming plate shapes the concrete to the exact cross-sectional profile. This plate, or extrusion pan, defines the road's crown or cross-slope, which is essential for water drainage. A properly crowned road sheds rainwater to both sides, preventing standing water that causes hydroplaning and accidents. Following the conforming plate, oscillating finishing beams smooth the surface to near-perfect flatness. These beams move side to side rapidly, screeding the concrete surface to precise tolerances. The result is a surface so flat that when tested with a 10-foot straight edge, variations of more than 1/8 of an inch are considered unacceptable. The entire paving machine operates as a single integrated system. Concrete enters at the front and a finished road surface emerges at the rear. The transformation happens continuously as the machine crawls forward at speeds between 3 and 15 feet per minute. Behind it, the road stretches out, perfectly formed, still wet, but already taking shape. Immediately behind the paver, surface texturing machines create the final ride surface. Burlap drags, artificial turf drags, or tined texturing equipment create micro-grooves in the still plastic concrete. These textures provide critical tire grip during wet conditions. The specific texture pattern is determined by State Highway Department specifications. Longitudinal tining uses metal tines dragged along the direction of travel, creating parallel grooves. Transverse tining cuts grooves across the travel direction. Diamond grinding done after the concrete hardens creates the smoothest, quietest ride surface available. Each method has specific advantages for different traffic speeds and climate conditions. Curing begins immediately after finishing. The exposed concrete surface must not dry out too quickly, or the chemical hydration reaction will be incomplete, resulting in weak, brittle concrete. Liquid curing compounds are sprayed onto the fresh surface, creating an invisible membrane that seals in moisture, allowing proper strength development over 28 days. In some conditions, white pigmented curing compound is used. The white color reflects sunlight, reducing surface temperature during the critical early curing period. In extremely hot or windy conditions, wet burlap or cotton mats are placed on the surface and kept continuously moist by water sprinkler systems. Proper curing is non-negotiable. Saw cutting of contraction joints begins within 18 to 24 hours after placement. Specialized concrete saws with diamond blades cut narrow grooves at predetermined intervals, typically every 12 to 15 feet. These joints create controlled weakness planes where the concrete will crack as it shrinks during curing, rather than cracking randomly across the surface. The timing of saw cutting is critical. Cut too early, and the blade ravels the concrete edge, creating a rough, weak joint. Cut too late, and the concrete has already cracked uncontrollably on its own. Experienced crews monitor concrete temperature and hardness continuously, determining the precise moment to begin cutting for each section. Joint sealing follows after the concrete has fully cured. Hot poured or silicone sealant is applied to every joint, creating a flexible, waterproof barrier. These seals prevent water from penetrating beneath the slab, where it could erode the foundation or freeze and expand, causing damage. Joint maintenance is essential for long-term road performance. Quality control testing continues throughout and after construction. Profilograph testing measures the smoothness of the finished surface, generating a numerical score. Roads that fail smoothness specifications must be corrected through diamond grinding at the contractor's expense. Financial incentives reward contractors who achieve exceptional smoothness beyond minimum requirements. Core samples are drilled from the completed road to verify concrete thickness and density. Each core is measured and tested in the laboratory. If thickness is deficient, the contractor faces financial penalties or, in severe cases, must remove and replace the deficient section. There is no tolerance for substandard construction on American highways. The machines used in modern American road building represent decades of continuous refinement. Slipform pavers first appeared in the 1950s, replacing the labor-intensive fixed-form methods that had been used since concrete roads were first built in the early 1900s. Each generation of machine has been more precise and more capable. Today's GPS-guided pavers represent the cutting edge of construction automation. Three-dimensional machine control eliminates the need for physical string lines, reducing setup time and improving accuracy. The machine receives design data directly from the engineering model and adjusts itself continuously in real time. The road is literally built from a digital blueprint. Trimmer machines that prepare the base ahead of the paver are equally sophisticated. These machines automatically trim the granular base to exact elevation and cross slope using the same GPS guidance systems as the paver. The result is a perfectly prepared platform that ensures uniform concrete thickness across the entire slab width. Concrete batch plants are mobile industrial factories set up specifically for each road project. These computerized plants measure and mix ingredients with laboratory precision, producing hundreds of cubic yards of concrete per hour. Every batch is electronically recorded, creating a permanent quality record traceable to any specific section of completed roadway. The logistics of continuous concrete paving rival military supply chain operations. A typical interstate paving project requires a fresh truck of concrete arriving every 3 to 5 minutes, maintaining an unbroken supply to the paver. Dispatchers coordinate dozens of trucks from multiple batch plants, managing timing like air traffic controllers managing aircraft landings. If the concrete supply is interrupted for even 15 minutes during hot weather, the paver must stop and a construction joint must be created. These cold joints are weaker than continuous paving and represent potential failure points. The pressure to maintain continuous supply drives extraordinary coordination between batch plants, trucking fleets, and paving crews. Night paving has become increasingly common on American highway projects. Working between 8 in the evening and 6 in the morning allows crews to avoid daytime traffic congestion and take advantage of cooler temperatures that extend concrete working time. The entire operation runs under portable lighting systems that illuminate the work zone like artificial daylight. Intelligent compaction technology is transforming base preparation. Rollers equipped with accelerometers and GPS create real-time maps of soil stiffness as they compact. This data identifies weak spots that need additional passes and prevents overcompaction that can damage the soil structure. Every square foot of compacted base is verified automatically. The environmental impact of concrete road construction is increasingly important. Many modern mixes incorporate supplementary cementitious materials like fly ash or slag cement that replace a portion of the Portland cement. This reduces carbon emissions from cement manufacturing while often improving the long-term durability and chemical resistance of the concrete. Recycled concrete aggregate from demolished old roads is being used in new base layers and even in new concrete mixes. This circular approach reduces the demand for virgin aggregate and keeps millions of tons of demolished concrete out of landfills. American highway engineering is increasingly focused on sustainability alongside performance. The finished American concrete highway is engineered to endure 40 years or more of service, carrying millions of heavy vehicle loads through extreme temperature cycles and weather events. When properly built and maintained, these roads outlast asphalt alternatives by decades, providing the lowest life cycle cost of any pavement type available. What you see when driving on a concrete highway is just the surface. Beneath your tires lies an engineered system of precise layers, each serving a critical function. Steel transferring loads between slabs, drainage layers removing water, compacted foundations distributing weight, every component working together invisibly to keep you safe at highway speed. American road building engineers have turned concrete construction into a science so precise that a surface poured today will still be carrying traffic 40 years from now. The machines that make this possible are engineering marvels in their own right, moving factories that transform raw materials into infrastructure that connects an entire nation. What do you think about the precision behind American concrete road construction? Did any part of this process surprise you? Share your thoughts in the comments below. And if you enjoyed learning how these incredible machines work, hit subscribe and turn on notifications so you never miss another fascinating engineering story from this channel.